All right, so now I want to go over E4.4, which is solving exponential and logarithmic equations. Anytime we solve for logs and our unknown is inside the log, meaning I have log of, whatever's inside here. Notice we cannot take log of a negative and we can't take log of 0. The reason is because if you graph a log always looks like this, or a log looks something like this. Notice I can't plug in negative numbers and I can't plug in 0 because my function has an asymptote there. So it's never going to be negative, it's never going to be 0. So when we're solving for logarithms, if we get an answer that makes the inside number of our log negative or 0, we have to throw it out. Okay, so that's one thing we're going to have to check for. And then I went ahead and wrote in all the properties that we've gone over so far. Okay, I am going to throw in a new one and I'll remind you here in a minute. But I want to highlight this first one. The equations y equals log base a of x and x equals a to the y are equivalent. Remember we had this one-to-one property that said that if a to the x equals a to the y, then x equals y. Okay, this implies that. We have one like that for logs as well. We have one that says that if log of x, or here maybe I should say base a, I'll put it over here. If we have log base a of x equals log base a of y, as long as we have log base a and log base a on both sides with no coefficient on them and only one log term on each side, then we can drop the logs, and this means that x equals y. So notice we're going to use these a lot. As long as we have the same exponential base on both sides, we can cancel the base and make an equation from just the exponents. And the same thing is true with logs. If we have log base a and log base a on both sides, we can drop those and just have x equals y. Okay, so keeping those in mind, we're just going to go over a whole bunch of different examples of all the different methods we've learned and possibly add in some new ones. Okay, so anytime that we are solving exponential equations, the way that we're going to do it is by using the inverse, which is our log form of the equation, to get the variable out of the exponent. Okay, so anytime we have it in exponential form, the way to get a variable out of the exponent is to take the log form of it, because logs and exponents cancel one another when they have the same base. So let's look at a few examples here. This first one says log base 10, or sorry, not log base 10, 10 to the x minus 9 equals 2001. Okay, notice my variable is in the exponent, so I need to get it out of the exponent. The only way to do that is to get rid of that 10. So if I have exponential base 10, I'm going to take log base 10 of both sides. Okay, log base 10 is just our regular log. I'm not going to write the little base 10. So my log base 10 and 10 will cancel, and I'm left with x minus 9 equals log of 2001. Okay, and then here log 2001, that's just something we can punch into our calculator and get a decimal answer for. So to go ahead and solve this for x, I'm going to go ahead and add 9. So I end up with x is equal to log of 2001 plus 9. Now I put parentheses around this so that you know to do this piece first and then add 9 to it. Okay, and since this is log base 10, I can use the log button on my calculator. Okay, so do log 2001, and then whatever that equals, add 9. We should get something like 12.30. Okay, notice here in our instructions it says round to the nearest hundredth, so I'm going to go ahead and round to 2 decimal places. Let's look at another one. The second one is the same idea. My unknown is in the exponent, which means I need to get rid of my exponential base. Now on this one, I don't just have e to the 3x, I have a 2 there. So I'm going to get rid of that 2 by dividing it off first. So I have e to the 3x is now equal to, if I do 145 divided by 2, that gives me 72.5. Then to get rid of exponential base e, I take log base e, which remember log base e is ln. So I'm going to take the ln of both sides. ln of e to the 3x is equal to ln of 72.5. My ln and my e will cancel, which leaves me with 3x is equal to ln of 72.5. Okay, again, ln 72.5 is just some number we'll get when we plug in our calculator. So to get x by itself, I need to divide off that 3. Okay, so I do ln of 72.5, and I'll go ahead and write a few steps in here, which should give you 4.2835 and some more junk. And then we divide that by 3, which gives us 1.4278 and some more stuff. And then again, we're rounding to the nearest hundredth, which is our second decimal place. So this tells me that x is approximately 1.43. Okay. All right, let's go ahead and look at one more example, and then I will have y'all try one. So this next one's a little bit uglier. It has a lot more numbers, but still the same idea. So I'm going to go ahead and work this by first isolating the exponential base, which is our huge ugly thing here inside parentheses, because I'm solving for this t, which is stuck in the exponent. So just like the last one where we had to divide off the 2 first, here I need to go ahead and divide off my 3,500 because it is not part of my exponential base. 7,000 divided by 3,500 is 2, is equal to 1 plus 0.027 divided by 365, raised to the 365t. Now, here is where we normally figure out what inside this parentheses equal, and that's our exponential base. And then we would take log with that same base. Now, here we have something pretty nasty, and I don't want to take log base nasty of both sides. All I want to be able to do is get this out of my exponent. So to get it out of the exponent, remember we had something that said if I have log x to the a, I can bring this down, and this is the same as a times log x. I'm going to use this property here, which basically says as long as I have a log in front of my exponential, I can bring down the exponent. So here I'm just going to take regular log, because that will be easier to do on our calculator, and here I don't really care about the nasty. I just need a log there so I can bring down that exponent. So I'm going to do regular log base 10 of 2 equals log of my nasty here. And the whole reason I'm doing that is so that now I can bring my exponent down in front as a coefficient. So now I have 365t times log of this nasty thing, 0.027 over 365, is equal to log base 2. Log of 2. So now I just need to get t by itself. And to get t by itself, I just need to divide off the pieces that I don't need, or that I no longer need. Okay? So notice all these things are being multiplied together, right? I have log of nasty and I have 365t, which are all being multiplied. So to make this a little bit easier, I am going to go ahead and get a decimal for this. When you plug it into your calculator, make sure you save all the decimal places so that your answer is most accurate. Okay, so I'm going to go ahead and write this as 365t times log of, if I do 0.027 divided by 365 in my calculator, that gives me 0.00007 and some more stuff. And then I add 1 to it, which gives me 1.00007 and some more stuff. Make sure you leave all the decimals in your calculator. Now I'm going to go ahead and divide off the pieces I don't need. So the pieces I don't need are 365, right? And then I also don't need log of mess. So I'm going to do it in 2 steps. I'm going to go ahead and divide off my log of the mess. You can do this all in 1 step if you want, but I'm going to do it in 2 just to make it a little bit easier. Okay. So here's my first step. I'm going to divide off the log of that horrible number so we can stop typing it into our calculator. Okay. And then I'm going to go ahead and work this out. Okay. If I do log 2 divided by log of 1.000, all that mess, okay, I should get something like 0.3010 and some more stuff is equal to 365t. Okay, now all I need to do is get rid of my 300, oh, I'm sorry, I didn't write this out. I wrote this out in too many steps. This is just log 2. If I do log of 1.00007, I end up with 3.212 and some more stuff. Sorry, I wrote out more steps than I thought. So I'm going to go ahead and bring this over here. This was a side note. So when I divide my two numbers on the left, I should end up with 9,370.66 and some more stuff equals 365t. And now to get t by itself, all I do is divide off my 365. Okay, which gives me t is equal to 25.673 and some more stuff. And remember, our instructions back on the last page said to round to the nearest hundredth, which is 2 decimal places. So here this means that t is approximately 25.67, and I'm guessing it's years because it says time, but I'm just going to leave it without a label. Okay. So this one was a little bit different, one because we had a big nasty exponential base here, but also because it was a little bit more difficult to work out, right? So we still isolate the exponential base by dividing off the 3,500, and then here we need to take log of both sides to get that exponential down as a coefficient. And then from there, it's just manipulating with our calculator, right? Simplifying each step, trying to get that t isolated all by itself. So I'm going to give y'all a few minutes to do this next practice problem, and then we'll go over it in just a second. All right, so on this practice problem, it's kind of the same idea. I need to get rid of my 3,500 first so that my exponential base e is isolated. When I divide off 3,500 from both sides, I end up with 2 is equal to e to the 10r. And then to get rid of e, I just take ln of both sides. When I take ln of both sides, I have ln of 2 is equal to 10r, and then I just divide off my 10. Okay, ln of 2 divided by 10, I can do in my calculator, which gives me 0.0693, and then I just round it to 2 decimal places, which gives me r is approximately 0.07. Okay, so let's look at some more. On these next ones, we're going to try to solve logarithmic functions. So notice on all the ones we just did, we had an exponential function, and we took the log of both sides to get the variable out of the exponent. Now we're going to do the opposite. We're starting with a logarithmic function, so to get rid of the log, we're going to take the exponential form. So I'm going to say use the inverse, okay, which is the exponential form, to get the variable out of the log. And I'll refer to this as changing forms. I probably have said this before and not really specified. When I say changing forms, I mean if it's in log form, we're going to change it to exponential. If it's in exponential form, we're going to change it to log form. Okay, so let's go ahead and look at some examples. Here I'm solving for log base 16 of x equals negative 3/4. Now, remember what we talked about at the very, very beginning. We cannot have log of a negative number, and we cannot have log of 0. So anytime our unknown is inside the log, that means we're going to have to check our solution. Okay, so I'm going to just ignore that for now, and I'm just going to use a pink arrow to remind me to check my solution because my x is inside the function. Now I'm going to worry about getting rid of this log base 16. To get rid of log base 16, I'm going to use exponential base 16, and I'm going to raise my equation up into the exponent. Okay, as long as I raise it using base 16 on one side, as long as I do it to the other side, I still have an equal statement. So my 16 raised to the log base 16 will cancel, which gives me x is equal to 16 to the negative 3/4 power. Okay, in our 118, we went over rational exponents. Remember, rational exponents represent power over root. So first, I need to make sure that this is a positive exponent by moving this feller down to the denominator. So this will give me 1 over 16 to the 3/4 power. Okay. And then remember, the top number is power, the bottom number is root. So I have 1 over, I'm taking the 4th root of 16, and whatever that equals, I'm cubing it. The 4th root of 16 is 2, and when I cube 2, I get 1/8. So that's my solution. Now remember, I use this pink arrow to remind me to check. I have to check to make sure my inside number, which here is just x, stays positive, meaning it can't be 0 and it can't be negative. So notice if I were to plug in x equals 1/8 into x, that works, right? Because 1/8 is neither positive nor 0. So this is my solution. Okay, let's look at another one. Looking at another one, notice again my unknown is inside the log, so we have to make sure at the end that the inside numbers of my log stay positive, not 0, not negative. So I'm going to go ahead and get rid of log base 7 by using exponential base 7 and moving my equation up into the exponent. So 7 raised to the log base 7 of 3x equals 7 to the negative 1. My 7 and my log base 7 will cancel, which leaves me with 3x is equal to 7 to the negative 1 power. Now again, I don't want to leave it as 7 to the negative 1 power. I want to move it down, but I'm going to go ahead and finish solving first. To get x by itself, I would divide both sides by 3, so that cancels off. So I end up with 7 to the negative first power over 3. Now again, we don't want negative exponents in our answers, so I'm going to take this 7 to the negative 1 and move it to the denominator, which gives me 1 over 3 times 7, and then I can simplify that to just get 1 over 21. Now I used a pink arrow to remind me to check my inside numbers. So notice my inside number here is 3x. If I were to plug 1 over 21 into 3x, I would do 3 times 1 over 21, which reduces to 1/7, which is neither negative nor 0. So since I got a positive solution, then I can use this answer. So my solution is 1 over 21. Okay. Let's look at another one. This one, same idea, but here I don't just have log of some number, right? Here I have 3 times the log. I can't have a coefficient when I change forms, so I'm going to go ahead and just divide off that 3. When I divide it off, that leaves me with log base 2 of x minus 1 is equal to 2. And now I can get rid of my log base 2 by raising it into the exponent using exponential base 2. So 2 raised to the log base 2 of x minus 1 is equal to 2 raised to the second power. I do this so that my log base 2 and 2 will cancel, which leaves me with x minus 1 is equal to 2 squared, which is 4. And then all I have to do is add 1 to both sides, which gives me x equals 5. Okay, I forgot to put my pink arrow, but I'll go ahead and write it in. Notice my unknown was inside the log, which means I need to check my inside number, which here is x minus 1. If I plug my answer, which is x equals 5, in here, 5 minus 1 gives me 4, which is not 0 and not negative. So since it's positive, x equals 5 is my solution. Okay, not too bad, hopefully. I'm going to look at 2 more, and then I'll have y'all try some. So notice on this one, there's actually 2 ways to do it. I could go ahead and take exponential base 3 so that those would cancel, or, which we've seen that before, so I'm going to do it a little bit different way. Notice here, we have log base 3, and then my inside number happens to be a power of 3. So what I'm going to do is I'm just going to replace this 9. Okay, I know that 9 is the same as 3 squared, so I'm just going to substitute that in. So this gives me log base 3 of 3 squared raised to the 2x equals negative 2. And now remember, when we have a power raised to another power, we multiply them. So this is log base 3 of 3 to the 4x equals negative 2. And now I have log base 3 of 3. Those are inverse functions, so they cancel, which leaves me with 4x is equal to negative 2. And then all I have to do is divide off my 4. So this tells me that x equals negative 1/2. Now notice I didn't draw a pink arrow on this one. The reason is, although my x looks like it's inside the log, it's actually an exponent. And it's okay to have negative exponents, it's okay to have 0 exponents, and it's okay to have positive exponents. As long as the variable is in the exponent, we don't have to check our solution. Okay, if the x was down here like where the 9 is, then we would have to check our inside number. But here my inside number is 9. That 9 is never going to change randomly to a negative or a 0 regardless of what the exponent is. So I don't need to check my answer. I can just say x equals -1/2. Okay, I want to look at another one. Some of y'all might be able to solve this one just by looking at it. If you're not sure, I'm going to go ahead and work it out. This says log base 3 of -1 equals x. Now, x is already isolated. We already have it solved for x. We just need to simplify this side. So we can't just plug this into our calculator because it's base 3. And we only have a log button and an ln button. So we are going to do change of base. Remember, our change of base formula looks like if we want to go from log base b of x, we can do that into ln or log. We can change it into one of the bases we have a button for on our calculator by doing log of the inside number divided by log of the original base. Okay, so I want to change these to base 10. So I'm going to do log of my original inside number, which is -1, all over log of my original base, which is 3. Now this I can plug into my calculator, but notice when you plug in log of -1 into your calculator, it should give you an error. And the reason is, when you do logs, remember, they have an asymptote at x, at x equals 0. Which means that they can never touch or cross 0. So notice if I go to where -1 is on these graphs, right, I can't trace -1 up and have a picture on this graph. It's undefined. Okay, this is also another example of why we can't have a negative inside a log. We can't have a negative inside the log. We can't have a 0 inside the log, because notice if you look at my pictures over here, negatives and 0 are not on my graph. They're not defined. So here I have no solution. Okay. All right, so there are 3 problems for y'all to try. I will give you a minute to work those and then we'll go over them. All right, so notice on this first one, we had a log base 1/3 of 3. Some of y'all may have seen that you could write 3 as 1/3 to some power, which is how I worked it over here on the right hand side. If you see that you can write 3 as 1/3 to the -1, then you can change that like I did here and just cancel those out automatically. And it makes it really easy to solve. You just divide off your negative and get x equals -2. If you didn't see that right away, which most of you didn't, to get rid of log base 1/3, we move our equation up into the exponent using exponential base 1/3. And then our 1/3 and our log base 1/3 cancels, which leaves us with 3 to the x equals 1/3 squared. Now 1/3 squared is 1/9. Okay, so what I'm hoping for is that I can write both the left and the right hand sides with the same exponential base. So 9 I know is 3 squared. So I'm going to go ahead and write this as 1/3 squared. And then to get them both with base 3, I'm going to move that 3 squared up to the top, which gives me 3 to the x equals 3 to the -2. And now that they both have base 3, I can cancel those 3's, which leaves me with x equals -2. Okay, so that was the first one. Let's look at the second one. The second one, I have log of x to the 10th. Now, there's no base written there, so it's an implied base 10. So I'm going to take 10 raised to the log base 10 on both sides. Okay, when I raise it up into the exponent, my log and my 10 cancel, and I'm left with x to the 10th equals 10 to the 10th. Now, if some x raised to the 10th power is the same as 10 to the 10th power, then that means x has to equal 10. So we've seen ones like this before. We've had something like 10 to the x. Whoops. Goodness. We've had things before like 10 to the x equals 10 to the 10, right? And then we could cancel these, and that means x equals 10. The same is true if it's the bases. If some base raised to the 10th power equals 10 to the 10th power, then that means the bases must be equal. Okay, so that was another play on our rule we had. The other way you might have done this is, notice I have log of x, and I have a 10 in the exponent. I could bring that exponent down as a coefficient and then divide it off, which will give me log of x equals 1. Okay, and then I can use the 10s to get rid of it. Again, my 10 and my log would cancel, and I'd be left with x equals 10 to the first power. Notice I do have a pink arrow here, so I would have to check this one to make sure my inside number, which is x, remains positive. And obviously if I plug in x equals 10 into x, I get 10, which is neither 0 nor negative, so that solution works. Okay, let's look at the last one, number 3. Okay, on number 3, the first thing I have to do is isolate the log, so I divide off the 5 on both sides, which leaves me with log base 4 of x plus 6 equals 2. Then to get rid of log base 4, I move my equation up into the exponent using exponential base 4. So my 4 and my log base 4 will cancel on the left, leaving me with just x plus 6, and on the right I'm left with 4 squared. So I have x plus 6 equals 16. I move my 6 over, which gives me x equals 10. And I forgot to put my pink arrow, but notice my unknown came from the inside number, so I would need to check. My inside number is x plus 6. So if I plug in my solution, which is 10, and I plug it in here, 10 plus 6 is 16, which is not 0 and not negative. Therefore, I can use my answer of x equals 10. Okay. So I want to look at a few more examples to get a little bit more complex, not horribly so, and then I'll let y'all practice some more. Okay, let me scroll down here. So here it's the same idea. We're still getting rid of logarithms using the exponential base. Okay, here it says using a calculator if necessary. That means that some of these don't turn out pretty. It also says round to the nearest hundredth, which is almost a sheer sign that we are going to have to use our calculator, and it's not going to be pretty. Okay. Here we have ln of x plus 1. I notice that my unknown is on the inside number. If it's on the inside number, then that means at the end I'm going to have to check my answer to make sure x plus 1 does not turn out to be 0 or negative. So let's go ahead and solve. To get rid of ln, I'm going to take e on both sides and raise my equation up into the exponent. So e to the ln of x plus 1 will cancel, leaving me with just x plus 1. On the right hand side, I end up with e to the third power. Now in order to simplify this, most of you have an e to the x button on your calculator or an e button. Okay, so you're just going to raise e to the third power, and I'm going to go ahead and just do that really quick. E to the third power gives you something like 20.0855 and some more stuff. And then to go ahead and solve for x, I just subtract 1. When I subtract 1, that gives me 19.0855 and some more stuff. We round to the nearest hundredth, which is our second decimal place, which means that my solution is approximately 19.09. And then don't forget to check your answer. If I plug in 19.09 and add 1 to it, I end up with 20.09, which is neither negative nor 0. So this solution works. Okay. Let's look at another one. Same idea. Okay. This one, we're still dealing with ln's. Notice ln and e are inverse functions. So anytime you have an e inside an ln, or an ln in the exponent of an e exponential base, those will cancel. So right away here, since I have ln of e, I can go ahead and just get rid of that. I can just cancel that out. Okay, which leaves me with 2 times x equals 5.6, and then all I have to do is divide off my 2. So I get x is equal to 2.8. Okay. Notice here the x was not inside my ln. I mean, it was, but it was an exponent, right? It wasn't the inside number. So since it's in the exponent, I don't need to check my solution. I can leave it like that. Okay. Several of you have stated that it bothers you that this exponent, this x, comes down into a regular number. So at this step, what you could do is take 2 ln e to the x, and we have that rule that says you can bring this down as a coefficient. So you could write this as 2x ln e equals 5.6. And then when you cancel those, it's easier to see that's just going to become 2x. Okay. Either way, it's completely fine. There's about 4 different ways to work any given log or exponential problem. So if you don't work it exactly the way I do it, or another way makes sense, as long as you do it correctly, then I am okay with that. Okay. So let's look at another example. Here I have log base 9. Now notice here my inside number does contain a variable. So at the end I am going to have to check to make sure that 2x minus 1 stays positive. So to solve this, I'm going to use exponential base 9 and move my equation up into the exponent on both sides. So 9 raised to the log base 9 cancels, which leaves me with 2x minus 1. And on the other side, 9 squared gives me 81. I solve for x by adding 1 to both sides, which gives me 2x equals 82. And then divide off my 2. Which gives me x is equal to 41. Now before I circle my answer, I must check x equals 41 over here. If I plug 41 in, 2 times 41 is 82, minus 1 gives me 81, which is positive. It's not 0, it's not negative, so this solution works. Okay. All right, so there are 3, I believe, yes, 3 for y'all to try. I'll give you a minute, and then we'll go over them. All right, so on the first one, notice here x is almost completely isolated. All I have to do is divide off the 3. Log 19 I can do in my calculator, and then I take that number and divide by 3, which gives me 0.42625 and some more junk, and then I just round it to the nearest hundredth, which gives me 0.43. Okay. Notice here the unknown was not inside my log, therefore I did not have to check my answer. Okay. On number 2, I do have to check my answer, right? Inside my inside number of my ln, I have an x. So I first need to get rid of my ln by taking e and raising my equation up into the exponent. So I have e raised to the ln of 2x equals e to the negative 1. Okay. And then to solve for x, I just need to divide off my 2. Now here, I could take this e to the negative 1 and move it down into the exponent if I mean into the denominator if I wanted to. But since I have an e button on my calculator, I'm going to go ahead and just raise e to the negative 1 power, which gives me 0.367 and some more stuff, and then divide that by 2, which gives me 0.18393 and some more stuff. And then I check to make sure my inside number stays positive. So here my inside number was 2x. If I multiply 0.18 by 2, it stays positive, it stays non-negative and non-zero. So that is an okay solution to have. Okay. And then on number 3 was tricky. If y'all did it, I am proud of you. My lecture classes did not like this one. Okay, again, there is about 15 different ways to work this problem. So if you didn't work it the way I did, that's fine. First thing I do is isolate the log. So I'm going to go ahead and divide off 10, which gives me 3 is equal to log of I over 10 to the negative 12th power. Now, I'm solving for I. In order to solve for I need to get I by itself. Right now, it's stuck inside a log, okay? I can't cancel the log in the 10 because I would have to have 10 to some power. I couldn't have 10 times something or something divided by 10. So what I'm going to do is I'm going to break this up into 2 separate logs using the properties we learned last time of expanding and condensing logs. Here I have a division. Division expands into a subtraction of logs. So I'm going to do log of I minus log of 10 to the negative 12th. And then here notice log of 10 to the negative 12th. Log and 10 are inverses. Log base 10 and 10 cancel, which leaves me with a negative 12. Now because that's being subtracted, here the double negatives are going to become positive. So I have 3 is equal to log I plus 12. And now I can easily move that 12 over by subtracting to get negative 9 equals log of I. And now that I have log I all by itself, now I can use 10, exponential base 10, to get rid of that log. So if I raise my equation up into the exponent using exponential base 10, I get 10 to the negative 9 equals 10 to the log I. 10 and log cancel, which leave me with I is equal to 10 to the negative 9. Now, here normally we would just go ahead and multiply this out and get a decimal, but since I'm rounding my decimal places to the nearest hundredth, if I were to do 10 to the negative 9, that's 0.00000, like 8 zeros and then a 1. So if I rounded to 2 decimal places, I would get 0 because I wouldn't have any place value yet. So I'm just going to leave it as 10 to the negative 9. Okay, I don't think I assigned any that are quite this hard, but I wanted to throw this in because the next couple of examples that we're going to go over deal with expanding and condensing. So I wanted to see if I could jog your memory just a little bit on that so that hopefully it's not a complete shock when we start doing it on the next problem. Okay, on this next problem, I'm going to implement that rule that I told y'all about earlier. Okay, our new rule that says that if we have log base a of x equals log base a of y, then that means that x equals y. Okay, two things I want to point out. Number one, there is only one log term on each side when I write this rule here. Okay, only one log term on both sides. The other thing that I'm noticing is there's no coefficient other than a 1. So in order to drop the logs, like this little property says I can do, I have to make sure there's just one log term on each side and that there's no coefficient. So looking at this example, the first thing I need to do here is condense. Okay? In order to condense a subtraction, subtraction becomes division. So I'm going to write these two log terms as one log term combined. The positive term inside number goes on top, and the term being subtracted, its inside number goes on bottom. So I get log base 7 of 3x plus 2 over x equals log base 7 of 4. And now that I don't have any coefficients and I have just one log term on both sides, I can drop the logs, which says that 3x plus 2 over x equals 4. Okay? And now I can solve by cross multiplying or clearing fractions. I'm going to multiply both sides by x so that I can cancel that x on the left-hand side, which leaves me with 3x plus 2 is now equal to 4x, and then I subtract my 3x. Okay, so easily enough, we end up with x equals 2. Now before I circle my answer, notice I had x variables on 2 of my inside numbers, so I have to check to make sure those stay positive. So I have to check 3x plus 2, and I also have to check x. So when I plug in my answer, x equals 2, into this first one, 3 times 2 is 6, plus 2 is 8. Okay, that's not 0 and it's not negative, so that one works. And if I plug 2 into x, I just get 2. So notice here, since it worked for both, then x equals 2 is my solution. If you have more than one inside number that has a variable, it has to work for every single one in order for you to use that solution. Okay, so let's go ahead and look at another one or another couple, and then I'll have y'all try some. Okay, so on this first one, or second one I guess, we again need to condense. We have two log terms on the left, so I need to condense. Addition condenses to multiplication. So this gives me log base 4 of x minus 3 times x minus 2 equals log base 4 of x plus 1. Okay, now I have log base 4 of something equals log base 4 of something, so I can cancel those, which leaves me with x minus 3 times x minus 2 equals x plus 1. And now in order to solve, I need to FOIL everything out and move it all to one side. Most likely on these you have to factor or use quadratic formula. I don't care which method you use as long as you remember to check your answers. Okay, when I FOIL over here on the left hand side, x times x is x squared, x times negative 2 is negative 2x, negative 3 times x is negative 3x, and negative 3 times negative 2 gives me positive 6. Okay, is equal to x minus 1, sorry, x plus 1. So I need to move my x and my minus 1 to the other side so that it's all equal to 0. So I have x squared, and I have 3x terms to combine. Negative 2, negative 3, and negative 1 which gives me negative 6x. And then I have positive 6 minus 1, which is positive 5. Okay, I'm going to try sum product. So I need something that combines to negative 6 and multiplies to positive 5, which I can use here negative 5 and negative 1. And since my leading coefficient is a 1, I can use my shortcut, which says that these two numbers are my factors. So this factors into x minus 5 times x minus 1. Then I just set each one equal to 0, so that gives me x equals 5 and x equals 1. Now, because I have variables on the inside numbers of my logs, I have to check to make sure that they all stay positive. So I have to check x minus 3, I have to check x minus 2, and I have to check x plus 1. Okay? When I plug my solutions in, 5 minus 3 is 2, that works. 5 minus 2 is 3, that works. And 5 plus 1 is 6, so that works. So x equals 5 is a solution. Now when I plug 1 in, 1 minus 3 is negative 2, which does not work. So x equals 1 is not a solution. So in my math lab, if you were given a problem like this when it asked you to enter your answer, the only answer you would put in is x equals 5. Okay. Let me look at one more and then I'll have y'all practice. This one, it almost looks the way I want it to. It has an ln, just one ln term on each side. However, one side has a coefficient. And I can't just divide it off because then I would have a number on the other side. So the way to get rid of a coefficient is to stick it back up in the exponent. So this looks like ln of x plus 3 quantity squared equals ln of 12x. And now that I just have one ln term on each side and no coefficients, I can drop my ln's. So this leaves me with x plus 3 quantity squared, which I'm going to write as x plus 3 times x plus 3 equals 12x. Then I'm going to FOIL it all out and move it all to one side. So x times x is x squared, x times 3 is 3x, 3 times x is 3x, and 3 times 3 is 9. And then I need to move my 12x term to the other side so that it's all equal to 0. So I have x squared. When I combine my 3x terms, 3 and 3 give me 6, minus 12 gives me negative 6x, plus 9. Again, I'm going to try sum product. If sum product doesn't work, then you have to use a quadratic formula. Here, to multiply to get 9, to combine to get negative 6, I can use negative 3 and negative 3. Again, because my leading coefficient is a 1, I can use my shortcut. So I know this factors into x minus 3 times x minus 3. And because they're the same, I'm just going to solve it once. We get x equals positive 3. Now, to make sure I can use this solution, I have to check to make sure that my inside numbers stay positive. So I have to use x plus 3 and 12x and plug my solution in. Now, if I plug 3 into x plus 3, I get 6, so that works. If I plug 3 into 12 times x, so 12 times 3 is 36. Not negative, not 0, so my solution works. Okay. All right, so there is 3, or maybe there's just 2. Nope, there's just 2. 2 for y'all to try. I'll give you a minute and then we'll go over them. All right, so on this first one, we have to condense first because we have an addition that condenses into multiplication. Once I've condensed it, I can drop my logs, or my ln's here. I FOIL out the left-hand side and move the right-hand side terms over. So when I combine, I get x squared minus 2x minus 8, which I can easily factor using sum product into x minus 4 and x plus 2. Which means that my solutions are x equals 4 and x equals negative 2. Now when I check my solutions, 4 works just fine in every single inside number, but x equals negative 2 doesn't work. If it doesn't work in one of them, I can't use it at all. So the only solution I would have on number 1 here is x equals 4. Let's look at the second one. On the second one, again, I need to condense. I need to condense an addition, which condenses into multiplication. Once I condense it, I can cancel my logs on both sides. When I FOIL out the left-hand side and move my terms from the right-hand side, over to the left, I'm left with just x squared minus 16, which is a difference of squares. So that factors into x plus 4 times x minus 4. So my two solutions are negative 4 and positive 4. Okay. When I check my solutions, neither one of them work. If neither one of them work, then my answer is no solution because I can't use either of the ones that I got. Okay. All right. I have one more problem type to show you. All right. So the last one we need to go over is the kind where we don't have logs on both sides. So on all those other ones, every single term had a log. Okay. If we're solving one that doesn't have, or has one term that doesn't have a log, we still work it the same way. We still need to condense so that we have just one log term. So starting off with that idea here, I want to go ahead and condense these two terms. I have an addition which condenses into multiplication. So this would give me log of x minus 2 times x plus 2 equals 2. Now, this looks exactly like what we did at the beginning of this section, right? We have log of something equals an exponential, or sorry, a constant. So to get rid of a log, I just use the exponential form, okay? So I'm going to use 10, because this is log base 10, and raise my equation up into the exponent on both sides. So that way my log base 10 and 10 cancel, and I'm left with x minus 2 times x plus 2 equals 100. Now, notice here, we still had to condense, okay? We still need to condense. The only thing that has changed here is we had to condense first, and then we solve it the same way. So I'm going to write something over here, and then I'll finish solving this. So if we have like log base a of x equals log base a of y, if we have logs on both sides, we can cancel that and just get x equals y. Here we couldn't do that because we didn't have a log on both sides. So you can't cancel here, so we change forms, okay? Logs on both sides, condense and cancel. Logs only on one side, condense and change forms. Okay, so let's go ahead and finish working this one out. When I FOIL this, I should get x squared plus 2x minus 4. Notice my x terms are opposites, so I'm left with x squared minus 4 equals 100. And since I don't have an x term, I'm going to solve this using the square root property. So I'm going to move my 4 to the other side, so I get x squared equals 104. And then to get rid of the x squared, I take the square root. Now when I do that, you have to remember plus or minus. So plus or minus the square root of 104. So the square root of 104 is 10.1980 blah blah blah. Okay, and I'm going to round it to 2 decimal places. So I get plus or minus 10 point. 2 decimal places would be this 9, which rounds up, so it would be just be 10.20. So I need to check x equals 10.2 and x equals negative 10.2. I need to check because notice my originals had unknowns inside the log. So I need to check x minus 2 inside number and x plus 2. If I plug positive 10.2 in and subtract 2, I get positive 8.2, so that one works. If I plug 10.2 into x plus 2, that works. If I plug negative 10.2 in, that one doesn't work. Okay, so x equals negative 10.2 is not a solution, and the only solution I get here is the positive 10.2. Okay, does that make sense? Let me look at one more, and then I'll have y'all try some. Okay, so on this one, the first thing I need to do is condense. Again, I have an addition. Addition condenses into multiplication. So I'm going to write this as 1 log base 4 term, and on the inside I'm going to have x minus 3 times 2 equals 3. Now I don't have a log on both sides, so you can't cancel this log. The way to get rid of the log is by changing forms. So I use exponential base 4 and raise my equation up into the exponent. Make sure you do it on both sides. So on the left-hand side, my 4 and my log base 4 cancel, and I'm left with x minus 3 times 2 is equal to 4 to the 3rd power. Okay, so I'm going to go ahead and simplify here. Distribute the 2, which gives me 2x minus 6, and 4 cubed is 64. and then I just solve. I add 6 to both sides, which gives me 2x equals 70, and then I divide off my 2, which gives me x is equal to 35. Now again, I did have one inside number with a variable, so I need to go ahead and make sure I check my solution to make sure my quantity x minus 3 stays positive. If I plug in x equals 35, 35 minus 3 is 32, so it works. So we're good. Okay, there's 2 for y'all to try. I'll give you a couple minutes and then we'll go over them. All right, so on the first one, I condense into my multiplication. Once I condense into my multiplication, I can then change forms. So I get rid of log by raising my equation up into the exponent using exponential base 10. And then I can solve using the square root property because I don't have an x term. So I move my 9 over, take the square root, don't forget plus or minus, and then I check both answers, both the positive and the negative answer. Only the positive answer works here, so I can't use the negative one. Okay. Same idea on number 2. When I work out number 2, I condense into multiplication. And then I get rid of the log by using exponential base 2. I can't just cancel the log because I don't have a log on the right hand side. So I use exponential base 2, which cancels my log out. And then my right hand side becomes 2 to the 3rd, which is 8. I move everything to one side and factor. When I solve, that gives me positive 8 and negative 1 as my solutions. Make sure you check your answers. When you check your answers here, notice the inside number becomes negative when I plug in negative 1. So the only solution I have here is x equals 8. Okay. All right. So it looks as though that's the end of your notes. I do want to do a couple of extra problems that are a little bit more advanced, just so you've seen it. It's probably not the level I would put on an exam, but I like to put them on the review just to give you some extra practice with your change of base and that type of thing, and just so you've been exposed to some harder problems. So I'm going to go ahead and just write in a couple more here. The first one I want to look at, I'm just going to call this more examples. Okay. Whoops, let me write a line right through it. More examples. All right, so the first one I want to look at is 5 to the 1 minus 2x is equal to 7 to the x over 7. Okay, now notice this is one that if I were to take the log of both sides, it's not going to get rid of both, right? I can't write 5 as base 7. I can't write 7 as base 5. So what I'm going to do is I'm going to use a different method of solving. I'm going to go ahead and just take regular log. We did one like this earlier, that one that had a horrible exponential base. When you can't take a base and get rid of both of them, then what I would do is just use the regular log button on your calculator. So here what I'm going to do is I'm just going to do log of 5 to the 1 minus 2x equals regular log of 7 to the x over 7. And the reason I do that is so that I can bring these exponents down as coefficients. So I'm going to end up with 1 minus 2x times log 5 is equal to x over 7 times log 7. Okay, and now remember, we're solving for x, so I want to get x isolated. Now right now I have an x stuck inside this purple quantity, and I have an x over here with my 7. So I'm going to refinagle a little bit. I'm going to go ahead and distribute this log 5 into both terms. So I end up with log 5 minus 2x log 5 equals x over 7 times log 7. Now the 7 on the bottom is kind of messing with me. I don't like it. So I'm going to go ahead and clear fractions by multiplying every single term by 7. If I multiply every single term by 7, it will clear that 7 off of that third term. So I'm left with 7 log 5 minus 14x log 5 equals, over here my 7's cancel and I just have x log 7. Okay. Now remember, we're solving for x, so every term that has an x in it I need to get on the same side. So I'm going to go ahead and add 14x log 5 to both sides to move that one over. Okay, because one's a log 5 and one's a log 7, I can't combine them, so I'm just going to leave it as it is equal to x log 7 plus 14x log 5. Okay. And now that all my x's are on the same side, I can get x by itself by factoring it out like a greatest common factor. Okay, how much room do I have left? I have, okay. So I'm going to go ahead and write 7 log 5 is equal to, if I take this x out, I'm left with log 7 plus 14 log 5. Okay. And now, notice, since x is by itself, all I have to do is divide off this horrible mess. Okay. Now, this horrible mess, notice because I used regular log, these are numbers I can just easily punch into my calculator to get an answer for. Okay. So that's what I'm going to do. I'm going to go down here and simplify it in a few steps. I'm going to pull out my calculator so I can work it with y'all. So on top, I'm going to go ahead and take log 5 and then multiply that by 7. So my top numerator value should be 4.8927 and some more stuff. On bottom, I'm going to do it in two pieces because I have a basic calculator. So let me go ahead and store this one. Okay, I'm going to do log 5, and then I'm going to multiply that by 14, and then I'm going to add that to log 7. Okay, so I'm just going to go ahead and write down here, I have log 7. When I did 14 log 5, I got something like 9.7855. Okay, so I'm going to go ahead and add log 7 to that, which gives me, on the denominator, 10.6306 and some more stuff. Okay, and now I'm going to go ahead and divide these two numbers. Okay, I'm going to write my x over here. So, I'm going to store this. So I'm going to do my 4.8927 number divided by my 10.6306 number, and what I end up with is 0.46025 and some more stuff. Okay, and then just like all the other ones we worked, I'm going to go ahead and just round this to 2 decimal places. And I'm going to rewrite it down here so I have room to write my other problem. So this is going to be approximately 0.46. Okay. Now remember, if we look at our original problem, our original unknowns were up in the exponent, so I don't need to check my answer. I can just leave it like that. Okay. So still the same type of problem. The only difference is we had 2 exponential bases which we could not write with the same base, so we used regular log to get the unknowns out of the exponent, and then we just move all of our terms around so that our x terms are all on the same side, and then we just factored out the x and used our calculator to solve. Okay. I'm going to show you another one, same idea. So on this one, let's try something like e to the 2 over x is equal to 11 to the 3x. Okay. Now this one is a little bit easier, I think, because instead of using regular log, I'm going to use ln for 2 reasons. One, ln, I have a button on my calculator, and 2, it'll at least get rid of one of the bases. So I'm going to go ahead and do ln of e to the 2 over x equals ln of 11 to the 3x. On the left-hand side, ln and e cancel, which leave me with just 2 over x. And on the right-hand side, I'm left with ln of 11 to the 3x. Now, here my unknown is still in the exponent. So just like the last example, I'm going to go ahead and now that I have a log, I can bring that exponent down in front as a coefficient. So this is ln of 11 equals 2 over x. Okay. And now I need to go ahead and solve for x. So I have x's everywhere, right? I have an x in front of my ln, I have an x in the denominator. So I'm going to go ahead and clear fractions by multiplying both sides by x to get that x out of the denominator. What that leaves me with is 2 is equal to 3x squared times ln 11. Okay, so I'm going to go ahead and work this out. Now, when I have all these things being multiplied together, I can reorder the way it's written. So I'm just going to write the 3 and the ln of 11 at the beginning, so it's easier to see that I can just divide off that piece that I don't need. Okay, if I divide off 3 ln 11 on one side, I have to divide off 3 ln 11 on the other side. Okay, so what that does, when I plug that into my calculator, I have 2 divided by, when I do 3 ln 11, it gives me something like 7.193 and some more junk equals x squared, which when I divide that out gives me 0.27802 and some more junk equals x squared. And then notice here, I'm not done solving because I have an x squared. So I'm going to go ahead and do plus or minus the square root of 0.27802 equals x. Now when I take the square root, what I end up with is plus or minus 0.5272 and some more stuff. Notice again, my unknown started out in my exponent, so I don't have to check my answers, and I'm going to go ahead and round my answers to 2 decimal places. So I end up with plus or minus 0.53. Okay, so again, just a couple more examples, more complicated examples of how to solve exponentials when the bases are not the same. Okay, that's the end of E4.4. So you should now be able to complete the My Math Lab assignment on that. Let me know if you have any problems.